In this video, we're going to be looking at kinetics, and we're going to be studying, what kinetics are. And a good picture that you see on the first page here are the turtle versus the human. And chemical reactions are similar in this manner, where you have some reactions that are slow, and you have some reactions that are fast. And what we're going to do is we're going to study the rates of those chemical reactions. That's basically what kinetics are. And this is going to be a multi-part video series, and this is just one part of this particular topic. So again, the definition for kinetics studies the rate at which a chemical process occurs. Besides the information about the speed at which reactions occur, kinetics also sheds light on the reaction mechanism. And mechanism is basically how a reaction happens. It explains what's taking place during reaction to give you that overall reaction. So there are several factors that will affect the rate of reaction. The first one, physical states of the reactants. So in order for reactants to react, the molecules must first come in contact with each other. And so when we talk about the different physical states, you have solids, liquids, and gases. Gases are more likely to interact with each other more than the liquids and the solids. So oftentimes solids are going to have a faster rate of reaction as compared to the other two, liquids or solids. Now the other thing you have to pay attention to is the homogeneity of the mixture. So if you have a reaction that has two different physical states, you might see that reaction is going to go a little bit slower than a reaction that would have all gases or all liquids or aqueous solutions. So these are just a couple things that you have to take consideration. So, what's the physical state, and is the reaction homogeneous or not? So another example would be concentration of reactants, and this should make more sense than anything else. If you let's say you had a kid and you took them to your parents' house. A lot of times parents like to give the kids candy. Well, the problem with that is that candy has sugar in it, which in turn makes your kids go haywire. So you tell your parents, don't give them any candy. But they do it because it's funny, because they want to watch the kids bounce off the walls. So the higher the concentration, the greater the effect is going to be on the reaction rate. And that's because as you add more reactants to the system, there's going to be more likely for them to collide. That was one of the first things you have to pay attention to, is concentration. How often are they going to collide? And the more collisions they have, the more possibilities that they're going to react with each other. And then that causes the reaction to go faster. Another factor is temperature. Temperature is an important player here. And as you increase the temperature, you decrease the temperature, what happens? You affect the kinetic energy of those molecules. And so if you increase temperature, you're going to make things go faster. The faster they're going to go, the more likely you're going to interact with each other. And that's what causes the rate of reaction to occur. And then if you want to make something last longer, well, you're going to decrease the temperature. So you've probably seen movies talk about cryogenic states where it's super cold temperature and they freeze a human body. And then by slowing down that reaction, which your body does have many reactions, as you slow those reactions down, you increase the longevity of that human body. And so some movies show that they could last up to 100, 200 years, and they bring them back out of that cryogenic state, and it's a totally different world at that point in time. So temperature plays a critical role in how fast a reaction takes place. Now, the last thing here is a catalyst. We're going to talk about catalysts at the end of this chapter, but for right now, in this video, we're just going to introduce what a catalyst is. Catalyst is something that speeds up a reaction by altering the mechanism. And so another important detail is our catalysts are not consumed. A catalyst will go in as a catalyst and it comes out as a catalyst. But like I said, we're going to save that that topic for the future. So for now, just there are 4 factors that affect the rate of reactions, and this is one of those factors here. Now, what we're going to jump into are reaction rates. So what is a reaction rate? Reaction rate is a change in the chemical species per unit of time. And so that unit of time is represented by delta T. And so we can look at it as just how much of something's present and how fast it takes place. And when I say it takes place, how fast it changes per time. So a rate of reaction, and Rxn is representing reaction, is equal to the change in concentration over change in time. Now the brackets here is representing concentration units, and that unit here is represented by molarity. Remember, molarity is moles per liter, and then time often is represented by seconds. So the units for a rate of reaction would be molar per second. Now you can look at the reactants or you can look at the products in this case. So here's a reaction where we're going to focus on the reactant. And what you're going to observe, and this is something that you always see happening, is that when your time is 0, you have the highest concentration for the reactants. But as that reaction proceeds, it's going to go down over time. And the question is, how much does it go down? And that really goes into the kinetics of that reaction. So now in this case, we're looking at C4H9Cl. And what happens here is it goes down a little bit, it keeps going down, and it keeps going down. But if you notice here, with the time, it's fairly quick to begin with, but then here it starts to change, and then here it starts to change more, and then here it changes more. So if we were to graph this, and we were to graph concentration versus time, what would we say? What we'd see is we would see an exponential decay. Now, once you get down to the bottom here, it starts to slope off, and the reason for that sloping off is the concentration becomes so small to the point where it takes a pretty good while for those reactants to find each other, to collide, then to react. And eventually it would possibly reach 0, but the odds of that happening would take an extremely long amount of time. And you can see here it took up to what, 10,000 seconds for that reaction to reach its end point at 0. So we could write the rate of reaction with respect to each of the reactants and products here. So if we were to write the rate of reaction with respect to the C4H9Cl, the way we'd write it is we'd have negative change in concentration of C4H9Cl over the change in time. The reason for that being, the negative sign tells you that you're dealing with a reactant and its concentration is going to go down over time. And then, the change in concentration is just a change in concentration from the final concentration to the initial. And then the change in time is basically how long it takes for that change to take place. And we could figure that out by looking at variable scenarios throughout this reaction here. So as you can look at what's been calculated here, so we see that average rate on the right hand side. And what we should just observe here, and this is the important thing that you're going to see, is that it's not a constant. It goes down, and that's because the concentration themselves and the amount of time it takes changes. And so the average rate of the reaction over each interval is the change in concentration divided by the change in time, like we were talking about on the previous slide. So again, it's it's those collisions that we're focused on here. The lesser amount of collisions, the longer it's going to take, and thus that the rate of that reaction is going to decrease. So we can plot the change of concentration over change in time here, and what we observe is an exponential decay, but what you also see, and I'm going to kind of highlight here, you see that the curve, it's not a curve continuously. There's a small portion in here that stays fairly constant, and this is where you're going to get your best rate of reaction. That's what's going to hold true for that reaction. Once this starts to change, you start to get this sloping off here. And now, one thing we can do is determine the rate of reaction by using the slope of a line tangent to the curve. And so that's just that you can figure out what the slope of that is at any point on this curve. But sometimes it's better to figure out a way to get a straight line, because it's a lot easier to figure out the slope of a straight line than it is for that of a curve. But you can see at this point in time, this would be the rate of reaction here. If we were to do the same thing here, it would be the rate of reaction here. And we would just figure out that based off the time at that point and what the rate is, or in this case, the concentration. So all reactions do slow down over time. So again, as we say, the best indicator for the rate of reaction is at the beginning of the reaction, because that's where you're going to have the least sloping off as what you see further down. So one other detail that we need to pay attention to is the stoichiometry of these reactions. And so stoichiometry, again, is based on off the balanced equation. And in this example here with the C4H9Cl, we see that the ratio is 1 to 1 as we go from the reactants to the products. Now, that means the rate of change, the disappearance of the C4H9Cl, is going to be consistent with the appearance of the C4H9Cl. And so, because it's a 1-to-1 ratio, as 1 mole of the C4H9Cl is reacted, there's 1 mole of the C4H9OH that's going to produce. So the problem that you see happening here is not the fact, in this case, that they're 1-to-1, but what if they were not 1-to-1? Then we'd have to be dealing with a ratio that we'd have to pay attention to. So what if the ratio is not 1-to-1, like this example here? We have 2 moles of HI on the left, and we have 1 mole of H2, 1 mole of I2. What we would see here is the rate of change would be negative 1/2 times change concentration of HI for every change over the change in time. It's equal to, now if we're just looking at I2 and H2, they're both the same in this case, but we set these equal to each other because the rates are dependent on how much of the reactants are going down compared to how much of the products are going up. In this case here, it's a 1-to-2 ratio. So as you produce 1 mole of the hydrogen, your concentration of the HI is going to go down by twice, and that's why it's 1/2. And we really should have 1/1 here, but we don't, because 1/1 is basically 1. It's positive for the I2 because the products are being reduced, and it's negative for the HI because the reactants are going down. So to generalize this formula here, this is a generic reaction where we have A plus B yields C plus D. The coefficients are going to be what you write as your fraction in front of the rates. And if you notice for the reactants here, we have -1 over A, we have -1 over B. The negative sign just tells you that it's reactant because it's going to go down. And then for the products, you have 1 over C and 1 over D. But keep in mind that these coefficients here, the lowercase letters, represent what you put in the bottom of those ratios. So a couple problems here we're going to work on. The first one here, over a period of 200 seconds, concentration changes from 0.06 mole to 0.042 mole. What was the rate of which O2 changes over time? Let's solve that. I'm going to give you guys a few seconds here to do that. So I'll come back in about 30 seconds. All right, so let's do this one together then. All right, we're trying to figure out what it was the rate of change for oxygen changing over time. So in this case here, we're gonna write out change of O2 over change in time is equal to the rate. Now the change in concentration, remember change means final minus initial, so we're going to have 0.042 minus 0.066 divided by, they say over a period of 200 seconds, so that's 200 seconds. So all we got to do is take the math here, subtract this 2 and divide by 200. You're going to have 0.024 divided by 200 seconds, smaller, and you end up with 1.2 times 10 to the negative 4 molar per second. Now you see that I lost my negative sign, and that's because this is a disappearance. So there should be a negative 1 over 1 here. So negative times that negative gives you a positive value. So that means for this change, you're going to have 1.2 times 10 to the negative 4 molar per second. So that would be the answer for that problem. Let's look at the second problem. So for the reaction below, the rate of change from N2O4 per time is found to be 4.2 times 10 to the negative 6 molar per second. Determine the rate of change for NO2 and O2. So what they're telling you is the rate is equal to the change in concentration of N2O5, this should be 5 here, per change in time is equal to 4.2 times 10 to the negative 7 molar per second. What we need to do is figure out the rate for the concentration of NO2 per time, and we also need to figure out the rate of change in concentration of O2 per change in time. The way we're going to go about doing this is we're going to look at the stoichiometry. Now, if you look at the stoichiometry here, you got 4 to 2 for NO2. So that means that twice as much NO2 is going to come out as compared to your 2 N2O5. And so we know the rate for the change of N2O5. That means that the rate of change of NO2 is going to be 2 times that. So we would take 2 times this value here. And keep in mind, that's the stoichiometry there, because you're producing 2 moles more, or 2 moles times what you start off with N2O5. And so you're going to multiply it by 2. And so that ends up being 8.4 times 10 to the minus 7 molar per second. Now the second one is the O2. Now if you look at the O2 and compare that to N2O5, well, you can see that instead of, so for NO2 it was multiplied by 2, now we're going down by half. So we would need to multiply this. So we multiply by this up here times 1/2, because it's half the amount being produced. Now we give you 2.1 times 10 to the minus 7 molar per second. So the rate of reaction depends on concentrations of the reactants. We can express this as a rate law, and that's what we're going to do in the next few slides. We're going to talk about rate laws, the concentration and rate. So you can gain a lot of information about the rate of reaction. And so just some general notes here. So we have a reaction of A plus B yields C plus D. We can say that the rate of this reaction is proportional. You can turn this the rate the equality sign into a proportional sign, and it's based off of the concentration of A to the m power times concentration of B to the n power. So this is starting to become what is called a rate law. And rate laws are what we use to help describe how a reaction takes place. It's the kinetics of the reaction. Now, this equality, this proportional symbol can be rewrote using equality, but now we're going to introduce a new symbol, K. And K is the rate constant. And rate constant is dependent on the overall order of the reaction. Now you say, what is the overall order and how you determine that? Well, M and N are the orders of reaction with respect to each of those chemical species. Now, the overall order of the reaction is equal to M plus N. So to figure out the overall order of the reaction, all you have to do is sum the exponents that you find for A and B. Not all reactions will have a B, but depending on the reaction, whatever the exponents that you find are, and they'll be found in two different ways. The first way is going to be determined experimentally, and that's where the next video comes into play. So for this particular video, we're done. So this is part one, and in the second video, which we'll call it part two, I'll go over how we determine the orders of reactions for A, B, whatever that is, and how we determine K from that. Thanks for watching.